as we all know, physics is an aspect of science that deals with everything that we do in our life. And for every activity that we do, the physicists, our scientists, they have came up with a law or a theory that guides the way every activity that we carry out is being monitored or studied. Like what I'm here to explain today is Hooke's law. And we all know a popular scientist called Robert Hooke performed an experiment on a spiral spring. He tried to observe what happened when a spring is expanded and when it contracts. He came up with a law the popular law that we call the Hooke's law, which says that provided the elastic limit of the spring is not exceeded, the extension caused on the spring is proportional to the force that is applied to the spring. I hope this is clear now. So that is going to be the background theory for what we are going to do today. Now, back to this experiment on Hooke's law. In our lab, we are going to perform this experiment. Is going to be divided into two parts. The first one is going to be going to be termed as experiment 6, which is Hooke's law status. And the second part is going to be experiment 7, which is Hooke's law dynamics. Now, based on statics and dynamics, what it entails is that for experiment 6, we are only going to look at the extension that's going to be caused on the spiral spring without setting the spiral spring on oscillation. So that is what we are going to do under experiment 6. For experiment 7 that we are going to discuss later, we are going to look at the extension and we are going to set the stretched string into vibration based on the number of oscillations that we want to take. We are going to look at that. So let me start with the first experiment, which is experiment 6, Hooke's law status. What are the instruments that we need for this experiment? We require a spiral spring for this. We require a spiral spring. We need a meter rule, a return stand. Then we have a pointer that's going to be indicating the extension on the meter rule. So I'll be able to get the extension that is being caused on the meter rule. Then we have set of masses with a mass angle. That is for experiment 6. Now, the background theory for this particular experiment is this. The theory. Based on Hooke's law, we have that the force is proportional to the extension, which implies that if you express force in terms of the mass, because we are going to make use of mass, that we are going to convert the mass to force. That is, mass times gravity is proportional to extension, which implies that if we remove the proportionality sign, we are going to have mass times gravity equals to Ke, where the K is the spring constant, or sometimes we call it the force constant. So that is going to be the theory behind the two experiments 6 and 7. Now, we now go straight to experiment 6. The first we do is to get the length of the spring. And how do you get the length of the spring? We note the position of the string, of the upper part of the spring, which is reading 5.5. And we take note of the base of the spring, which is also reading 18. So when we take the difference between the two readings, we are going to have this is the upper part of 5.5, the lower part is 18.00 centimeters. So the length of the spring will be the difference between x2 and x1, which now give us 12.50 centimeters. Now, we are done with that. Then we now go straight to the experiment now. Then for the experiment, we are going to look at the points our reference point for this experiment is now going to be the lower part of the spring, which is the 18 centimeters. So the first reading you have is when no mass is added to the spring. Our reading is now going to be when we have 0 mass, that's 0.0 gram. The corresponding increase we are going to notice is going to be the first reading, which is 18.00 centimeters. So when we added the 20 grams to this, we allow it to come to rest and we take the reading. The reading is now going to be the direct reading from the meter rule is now going to be our A1. When we have the second one, we allow it to come to rest. That will be our A2. Then the next one is going to be A3, A4, and for the last one, because we're going to be giving 100 grams. So for the last one, we're going to have A5. So when we get to this point, you have finished loading the mass. That is mass increasing. Now the next thing we want to do is to now come to the second column of the table, which is say mass decreasing. But for the mass decreasing, you should note that you are not going to start from the beginning here, because it is assumed that the spring is already loaded. So we now start removing it one after the other. So for the first reading from this, I'm going to start from the below, because this B5 corresponds to 100 grams, which is the maximum mass on the spiral spring. So for the first one we have, you take the measurement again. When you are fully loaded the spring, you take that to be your B5. Then the next, you remove one of the masses again. 100 minus 20 is going to be 80, so corresponding to 80. You're going to write it here. Then you remove again to come back to where there's no mass on the spring. The reason why you are taking your reading from the below is so that the value that corresponds to the actual mass. If you start from up here, that means you are recording for 100 grams against 0 gram. So that is that about this mass decreasing column. Then we now look for the difference, that's the scale, the mean scale reading. So the average of these two readings. Because when you look at this, the value here should be very close or almost the same with this. So the mean scale reading is going to be the addition and the mean of 18.00 and B naught. That will give you your C naught. Then the same treatment applies down the column here. Then the last one now, we have what we call the mean extension. X bar, the mean extension. How do you get the mean extension? You remember that we have our X naught, which is the reference point, the lower part of the string, which is corresponding to the reference point. So what we are doing is this: you are going to subtract that reference point, which is X naught, which is 18 centimeters, from C naught, the mean of the mass increasing and the mass decreasing. So that will give you your C naught minus X naught, which is also going to be represented in centimeters there. Then come to the second one, C1 minus X naught. So when you look at this column, X naught is constant because that is the reference point. So that is how we are going to calculate the mass, the mean extension for the spring. So when we are done with this, you are almost getting to the end of the experiment. Then what you now do next is this: you now go straight to the question. The first question says that plot the graph of X, that's extension, against the mass. These are the column for the masses, and those are the column for the extension. So we are going to plot the graph. That's the first question. Plot the graph of M against N, and from its slope, determine the value of the spring constant. To get this, you refer yourself back to the background theory, then you'll be able to answer that. The next one says, estimate the error in the values by using the normal method of drawing Walk's line. All this one has been explained in the preliminary stage of the experiment, introduction to the practical demonstration. We are going to see it there. Then the next one says, plot a graph of your length now against the mass M. Then state two precautions for the experiment, and there's a question that you need to answer. When the first of this is that about the experiment 6, which is the Hooke's law statics. That is everything you need to know about this, and other instruction in the practical manner. Thank you very much.